Hey everyone, today we're going to learn a concept called union find. Union find is a key component in computer science with lots of real-world application like image segmentation, where it groups similar colors into one group, to machine learning clustering, where it combines similar data points into groups. Today, we're going to look at the most important usage in our time, which is to solving LeetCode problems. So what is union find? As you can see, union find basically has two key parts, union and find. There are two operations. The key of the whole data structure is to implement an algorithm or a technique that we can implement both of them in an efficient time complexity. So for the union UV, it basically means that this operation will try to connect vertex U and vertex V together. It's acting like a bridge. For example, if I try to apply union U and V in here, assume this is U and assume this is V, and now they will have the same group, but all the others will have their own group. And find, on the other hand, identifies the group vertex V belongs to. The main technique used is path compression, which will make the find operation super efficient, but what it does is basically telling what the group that the vertex V belongs to. For example, each group will have a label. You can imagine this might be 1, 2, 3, 4, 5, 6, and if I apply find V here, it will return 1 because this is the group that this V belongs to. However, we can apply several union again. For example, I can union, let's call this vertex X. I can apply this union Vx again, and this three node now will have the same group number. So what I'm trying to say is that find U should be equals to find V should be equals to find X. So that's the whole idea of union and find. So let's take a look at the first example LeetCode problem. In this problem, you are given a list of integer arrays, and then each index I and j, they are connected if and only if their GCD greater than 1, where GCD is the greatest common divisor. So basically it's saying that two indexes are connected if they are co-prime. So how does union find come into the picture? So it looks like it is just an array instead of a graph. However, when it is asking this kind of possible to traverse anything, it seems like a connectivity problem, even though it is just an array. But if we treat each index as an node, something like this, if it is connect, then we will draw a line between them. And if it is not connect, then we don't draw a line between them. And then finally, we will just need to know if all of the index are inside one group. And this kind of relationship just gives us a big hint that maybe we should use union find. Another tip that I can give, or I can talk about, is that the constraint is usually very large when it comes to union find problem, because union find, as we mentioned, is a very efficient algorithm. So whenever we need to deal with union find, the constraint is pretty large, like 10 to the power of 5 in this case. And so that's pretty much it. There is some connectivity inside the problem that we need to know if everything is in one group or anything is connected somehow. And the second thing is that the input size is large, so combine two things, we're sort of certain that union find will be used in some cases. So let's try to find every divisor of each number first and see what can we do about it. So here should be, for 2, the divisor should be 2 only, because we don't care about anything that is 1, because the GCD we care should be greater than 1. So we don't care 1, even though 1 is also a divisor of 2. And for 3, it will have 3. And for 6, it will have 2, 3, and 6. Then for each divisor, we have an index for them. And then how about we try to look the other way around? We'd want to know for each divisor, which index does it appear on? For example, 2, it appears on index 0 and index 2, correct? Index 0 and index 2. And for 3, it appears on index 1 and index 2. And then for 6, because we don't have 4, we don't have 5, so the next smallest number that we care is 6. So for 6, it only appears on index 2. Now, if we draw them in a graph, we will have something like, this is the 0 index, this is the 1 index, this is the 2 index. For a 2 divisor, because they share the same divisor, index 0 and index 2 share the same divisor, which is 2, and it is also greater than 1. That's why 0 and 2, or anything else, if that appears on the same divisor 2, will all be connected. Then we can just iterate all the divisors one by one and connect everything that is on the same divisor. For example, this index 0 and index 2, they are having the same divisor as 2, so we're going to connect them. Let's draw that in a graph. So they are having the same divisor 2, so 0 and 2 is going to connect, and 1 and 2 is going to connect as well, and 2 is nothing to connect. But if we take a look at this graph, then you can see it is a connected graph. Everything can be connected to everything else. That's why we're returning true here. So that's basically the gist of the solution. And let's see how we can actually code this up. So first I'm going to create a union find class in line 1 to line 14 here. So basically what it does is to implement the find and implement the union and accept and AND as the signs of the union find structure. So all the magic happens in here on line 7, where we kind of find the root of the parent recursively, but at the same time, we do a recursion and also set the parent of it to the answer. So basically, after doing this line 7 and 8, everything will return just here. So after asking find in here, then all the path will just be something like this. This is before the execution of find x. Let's say x is here, and this is after. So as you can see, whenever I try to execute a find, it will try to complex the path into one path only. That's why this algorithm is very efficient, that is very close to 0.1 in practice. After creating the union find structure, I'm going to create another helper method which is called divisors, which just returning all the divisors given x. The implementation is easy. I'm going to start by 2 instead of 1 because we don't care about the divisor of 1 as described it in the problem description. Then we're just going to loop through everything, and if it is divisible I is equal to 0, it means that it is divisible, so we're going to append that to our answer and finally return an answer. This answer basically means all the divisors for x. Then, after having these helper methods and helper class, then we can start implementing our solution. First, we're going to do some base case. Then, if it is 1 inside the numbers, then we just have to make sure that the numbers only has 1 element. Because if we have more than 1 element than 1 inside the numbers, it means that 2 element, that 1 cannot connect to another element. So that's one base case we have to handle. And then we're going to initialize the union find structure with size n. N is the number of elements in the numbers. And then we're going to fill up the index of divisors dictionary. As I mentioned, the key of this dictionary is the divisor, and the value is a list of indexes that appear for this divisor. So in here, I'm just going to fill this dictionary. After filling the dictionary, we're going to iterate every dictionary key, which means every divisor. And for every divisor, we're going to check every index for that divisor. Then everything will connect to the first index. I will just use the first index as the group, but in practice, you can choose the second or you can choose the third, but it's more convenient for me to use the first because there might be only 1 element or 2 elements in a group, so I don't have to check for the length. So that's why I'm just going to choose the first index as the group number, and then everything will connect to this group for this index. And then finally, I'm just going to check if everything is on the same group. So if they are something not in the same group, it means that this particular I is not connected by 0. It means we should return false. If we iterate everything and everything is connected on the same group, then we just return true. This is the full code, and let's try to submit it. And there we have it. The solution is accepted. So for the time complexity, it is O n times square n times log star n. So basically it comes from here where we have to traverse every divisor, which could be n times square n of them, and then each of the divisor we have to apply a union, and the union will be log star n. As I mentioned before, this log star n is very close to 0.1, so that's why this solution can be accepted as well. And as for the time, for space complexity, there will be O n times square of n for this dictionary, basically. Hopefully this walkthrough has been helpful, and goodbye for now.